In this problem, we're given a velocity versus time graph. And we're asked, first of all, does this particle have a turning point? And the answer is yes, that it does. And the best way to see this is to visualize what this velocity curve represents. It starts with a velocity that has a magnitude of 5 meters per second in the negative x direction. And that magnitude is decreasing as it becomes less negative and goes to 0. And then the velocity starts to become positive. And it increases in magnitude to 5 meters per second, so it starts speeding up to 10 meters per second, and then 15 meters per second in the positive direction. So when the velocity versus time curve goes through 0, that's a turning point for the system. Next, we want to find the value of the position at several points in time. We're given that at time is equal to 0, it's at a position of 8 meters, and we want to know what the position is at the t is equal to 1, 2, and 4 seconds. We can find the change in position because it's the area under the curve in the velocity versus time graph. So this is a triangle if we look at the difference between 0 and 1 second, and the area under that triangle is 1/2 base times the height, so that's 1/2 5 times 1, or 2.5. And it's a negative since it's below 0, so the change in position is a negative 2.5 meters. At 1 second then, its position is 5.5 meters. So what is the position at t is equal to 2? Well, the change in position from 1 to 2 is going to be the area under the curve between time is equal to 1 and 2 seconds. Well, that triangle is the same size as the triangle before. It has an area of 2.5 meters, but it's positive, so the change in position is a positive 2.5 meters, and so it ends up back where it started. At 2 seconds, it's at 8 meters. And so you can think about the change between 0 and 2 meters, which is the total area, the area of this triangle plus the area of that triangle. They're the same size, one positive to one negative, so the net change between 0 and 2 meters is 0. The value is the same. Finally, we want to know what is the position at 4 meters. So let's look at the change in position. We can go from 1 to 4. That gives us a simple triangle. The change in position, the x is equal to 4 minus x is equal to 1, is in the area under the velocity versus time curve between t is equal to 1 and t is equal to 4. Well, that's 1/2 the base times the height, so that's 1/2. The base now is 3 seconds. The height is 15 meters, and so that's going to be 22.5 meters. So the change in position between 1 and 4 is 22.5 meters, which means that the position at t is equal to 4 is 28 meters. So we can find the change in position, which is the area under the velocity versus time curve, and then use that change in position to find the position at each of these times. So what does the acceleration look like as a function of time? Since the velocity versus time is a straight line, the slope of the velocity is the same throughout, which means the acceleration is the same throughout. And if we calculate that slope, it changes by 5 meters per second every second, so the acceleration is a constant 5 meters per second squared. What does the position versus time graph look like in meters? We have that table, so at 0 it's at 8 meters, then it comes down to about 5.5 at 1 second, then back up to 8, and then to 28. We know this is a parabola, so it's going to curve down and curve up like this. So given a velocity versus time graph, we can find the acceleration by finding the slope of the graph, and we can find the change in position by finding the definite integral, or the area underneath the graph between 2 points in time, and then use that change in position to find the location at different points in time.